Okay, so last presentation today. So my initial idea was to present how to approach the problem from a statistician's perspective. So what I had in mind when we started thinking about AstroGeoFit, and so how I approached the problem. But I thought that maybe you thought that the 4 first lectures were already how to approach the problem from a statistician's perspective. So I think, so I tried to interact as much as possible with you yesterday. And today I will try to make the link clearer, I hope, between what we said during the week and how to actually operate the algorithm. So, like every day, small recap of what we did. The first day we saw the AstroGeoFit model, and that it has 3 key ingredients: the astronomical forcing, which is a sum of periodic function, a time depth conversion parameterized by knots, and a correlated noise model, which is an autoregressive process. And we've seen also that defining a model is basically defining a likelihood, a probability distribution, and to estimate the parameters of the model, in particular the noise parameters and the astronomical parameters and the geological parameters at the same time, we can do it by maximizing this likelihood. This maximization is done with the genetic algorithm, so that's what we want to do, that's how we do it. And also, I want to stress that this model, although pretty robust, is imperfect and not completely general, so you need always to ask if it's suitable for your data. Oops. Yes. So in the third day, we've seen that just with the genetic algorithm, we can select the complexity of the models, and in particular, we want to answer 2 questions. Should we have a model at all? Is there some astronomical signal in the data? Or is it compatible with being pure noise? And there is another question, which is, if we think that there is an astronomical signal, what is the complexity of the time depth function we want? Okay, and I want to stress also that rejecting the null hypothesis is not a validation of the detection of an astronomical signal in principle. When you reject the null hypothesis, you just reject that the data is a certain type of noise. Estimation of uncertainties, we do it through posterior probabilities, where you need to define some prior information. Yes. It's super important to make sure that the MC-MC converges. And again, I want to stress that you don't want to put information from the data in the prior, because otherwise you're kind of converging to your preconceived idea of what the data is. Numerical methods, super important, this is really super important idea. If the convergence was perfect, if we had perfect numerical algorithms, it would already be difficult to interpret the data. If the algorithms don't converge, if your MC-MC algorithm stopped too early, if your genetic algorithm didn't find the correct solution, then you have no conclusion at all. So now let's move on to how this translates to a workflow with AstroGeoFit. So this is just, so Eugene already gave you some ideas. You don't have to do these steps in this exact order, but hopefully there will be some ideas that you can use in your practice of AstroGeoFit. So pre-process the data. We've already said that you might want to clip outliers. And also, you might want to detrend the data, because at the moment, there is no trend in the AstroGeoFit data. I've said it already. And now, select the model parameters. So, very simple remark. The fundamental frequencies here are given by these keywords in the AstroGeoFit configuration file. And I want to make just a couple of points about this. So the thing is, you have names for the frequencies and interpretations, precession, obliquity, and so on. But what the algorithm sees is this. So the fact that this is called precession, obliquity, or whatever, the algorithm doesn't know it. So if you have frequencies which are very close together, and Joseph showed me an example yesterday where you have several frequencies which are very, very close together, but some of them come from eccentricity, some of them from precession, some of in the case of Mars. So if they are inside the same peak of the periodogram, you don't have the resolution to disentangle them. So you will have a contribution from both of them, but you will not be able to say, well, you will have a collective contribution from both of them, and in that case you might want to fix those frequencies, because if you have frequency intervals that overlap, you might have in your genetic algorithm at some point some frequencies which are extremely close and which will, and since you need to invert a matrix with cosines, if the cosines have frequencies which are extremely close, the inversion will fail and it will create numerical problems. Also, very simple point. Suppose you have a single frequency in your data. The algorithm won't see the difference to double the frequency and to divide the sedimentation rate by 2. So in particular, I've seen one example yesterday where sometimes the genetic algorithm converged to one frequency, sometimes to another frequency, which was roughly half of the frequency, but the sedimentation rate was divided by, was doubled. Well, the inverse sedimentation rate was doubled. So this is something that shouldn't happen very often, but again, keep in mind that for you, it's very clear that this frequency has an interpretation, this frequency has the other interpretation, but if the sedimentation rate allows the algorithm to change a lot the time depth conversion, then it might select one or the other. Also, we've seen yesterday that the algorithm systematically optimizes the value of the amplitude and phase of the astronomical signal. So you can't put an upper bound or a lower bound in the current version of the algorithm on the amplitudes. They are always adjusted so that the data fits, so that the model fits the data best. So time as a function of depth. You want to define the number of genes, which is the number of knots that the genetic algorithm is going to try, as well as the lower and upper bound on the sedimentation rate. So again, depending on your bound, it might change drastically over the mean of the sedimentation rate over the data, and then you might have some frequencies which are selected or other frequencies. So pay attention to this range. So you select the flexibility with the number of knots. And here I just wanted to illustrate some. Suppose this is the sedimentation rate you want to adjust. In that case, you will need knots which are very, very close to model the fact that you have very sharp transitions. Or you might want to do this. But then you increase a lot the number of knots. So it means that they are free as well in the intervals. So, and we've seen in the AstroGeoFit paper that if we leave it as is, it's actually okay at detecting hiatuses. So you don't necessarily need to have super tight grids. Sometimes a regular grid will just do. So about the noise, we've seen that we have an IR2 noise which assumes that the autocorrelation has this shape. Another way to think about it is to say that the noise has a certain frequency power structure. It has power at low frequencies. But so the noise is going to try to explain what's going on at low frequencies. But if you have also astronomical signals at low frequency, it might create degeneracies, and the way the noise absorbs the low frequency is maybe not exactly what you want. So you could also try to maximize, instead of maximizing the likelihood, you maximize the R2 metric. In this R2 metric, there is no adjustment of the noise. You assume that the noise is the same everywhere, and you won't have a correlated noise at all. And at least in the context of exoplanets, which is my specialty, I've seen that with the best intentions, you put a correlated noise model, and it scoops planets which are obviously there. Because the noise is not perfect, the noise model is not perfect, so it starts absorbing signal at low frequencies, and in particular, it starts absorbing the planet. So, in doubt, you can also try with an R2 metric and see what it tells you. The thing you don't want to do is to pick the two based on the article you want to write. If it's just more convenient for you because the signal appears better here, it doesn't mean that it's true. It's just another element that you can of your analysis. So, another remark. In the way the algorithm is coded right now, not only the phase amplitudes of the astronomical signal, but also the noise parameters are fitted. So it means that the noise is always fitted to match the variance of the data. But the uncertainties on the other parameters are also proportional to the noise value. So, for instance, yesterday with Mengyao, we've seen that there was the genetic algorithm was pretty good. The solution was very good, but the error bars seemed inflated. But in that data set, you had very large excursions. So the noise is trying to fit those excursions to match the variance of the data. So it thinks that the noise is extremely high. But this is maybe just due to nonlinear responses of the geological data set. So you might want to try to clip the values which are extreme. You might want to try to change, to make the response more linear, to avoid these large excursions and have more realistic error bars. So this is my interpretation. Maybe this is not exactly what's happening, but this is something that could happen. In the noise parameters, you also need to choose the priors. You can choose uniform priors or Gaussian priors, and then you can choose the width. And I just want to say that you must keep in mind that this will, especially if you put uniform priors, it means that outside of these uniform priors, you assume that any value is completely impossible. It means that you are as sure as anybody has been ever sure about anything that these values are impossible. Maybe you are not that sure. So, and especially if the posterior is cut, is on the edge of the yes.
I didn't mind I just have a question.
Okay, I just so we've seen in the lecture 2 that if the posterior is cut, wants to go outside the prior bound, maybe your likelihood or your posterior has a problem. Yes.
Okay, I have a question.
Yeah.
When you are trying to linearize your data as a pre-processing tool. I do that. I take the log of the data to reduce the extreme values. But that has a consequence in that I'm using chemistry, right, XRF, which has a lower bound on its sensitivity. That means that when you take the log, you amplify the amount of area under the curve that is close to the detection limit of your technique. So the noise, the true noise that's involved with measuring the samples, is amplified. How is there a way to reduce the...
in that case, I would just clip the low values.
Just clip off the low values. But that creates a further non-linear process which amplifies, like, eccentricity, the low frequencies. Yeah, too bad.
I mean, the thing is, I think there is no general recipe. I think if you understand well what the model is doing, and you understand the limitations, you will find a way to change your data so that it kind of the model will give you more useful results.
So other thing I do is loss smooth.
Yes.
And that takes out some of the noise at the low level.
So you don't necessarily want to take some of the noise out because the noise is already modeled and you want to propagate the uncertainties. But you need to keep in mind that when you take the log, the signal-to-noise ratio will be higher I mean, it's like you're stretching, and we've talked about this also on the normalization of variance. If you normalize the data, then you also shrink the error bars. But yeah, if you keep in mind that the model is a sum of sinusoidal signals, the noise is an AR2 model. If I fit it, what part of the data is going to go to what part of the model, then you'll find a way to pre-process your data and most likely it will be minimal. In general, just the data as it is pretty good, but maybe there is a way to tweak it a little bit so that the results are more reliable. And it's all about more reliable results, not better results in the sense that, oh, I see better this frequency, yes. Yeah, and today, feel free to interrupt me. The idea is to answer all the questions you might have, to discuss. It's more of a discussion, yes.
Thank you. So you say when we normalize the variance, the problem is you shrink the error bars.
Yes.
Do you speak about the error bars of the measurements themselves, or the error bars of the noise in general?
Of the noise itself.
So including the error in the measurement, the Gaussian noise, plus the errors of plus the noise related to the climatic systems, like the autoregressive noise.
So I mean that in the data, the true noise was of this amplitude. Now, if you shrink the data, the true noise has this amplitude, and so this is the true noise. But your noise model assumes that the properties of the noise are the same everywhere.
Okay. And now, as far as I understand, it's related to the noise in the measurement. What about if the noise in the measurement is like 1% of the value itself? I mean, it doesn't really matter.
Yeah, it doesn't. Then in that case, it doesn't matter.
Which is the case for some, like when you measure the magnetic susceptibility, the error is very low compared to the value itself.
Yes. Okay. So actually, this is an important point. When I'm talking about the noise, I'm talking not about the measurement noise, or at least not only the measurement noise. I'm talking about the geological noise. Okay, I didn't think about it before, but the thing is, in your geological record, you have some signal of geological origin, which is not the astronomical signal. And the purpose of the term here is more than modeling the measurement noise, to model this process, this correlated process, which seems to affect the geological data, because when you take the periodogram of stratigraphic data, usually the power structure is like this. So there is a red noise component that you want to estimate. But yes,
maybe you can remind what is a red noise compared to a white noise.
So red noise means that the value of the noise at a certain depth depends on the value of the noise, is correlated with the values of the noise at other depths. The noise has a memory, which is what creates low frequency structures in the periodogram. If the noise had no memory of its past values, then you would just see a noise floor in the Fourier analysis. Actually, so I talked about the autocorrelation function. If you take the Fourier transform of the autocorrelation function, you will have the trend in the periodogram that you see because of that noise.
Maybe you should remind what is the autocorrelated function.
So the autocorrelation function, I don't have the formula here. I defined it in day 1. So you have your signal as a function of depth. You duplicate it, and you multiply the two. Then you shift one of the copies, you multiply the two. You shift one of the copies, you multiply the two. So the thing is, as you shift away, you will have a value of depth which has nothing to, which is far in indices, which is several indices later, and it will have forgotten the value of the noise at the depths before. So if you shift since your noise is correlated, it has some temporal structures. If you shift it a little bit, it still looks like the initial copy. But as you move away, they become more and more different. So that's what the autocorrelation function captures. It's like at first, as zero lag, you just have the noise exactly similar to itself. And as you shift the copy, then the noise seems less and less similar to itself. But this behavior that you see in the autocorrelation is found when you take the Fourier transform in the spectrum. That's what creates the slope in the spectrum. So yes, another way to think about here what we are doing is kind of equivalent to what's being done in some analysis of geological time series, where you have a filter on the spectrum to estimate the local value of the noise.
Hi, Nathan. I was thinking yesterday that a solution to compute the algorithm faster could be to decrease the resolution or subtract some of the spectrum of my data, because I was realizing that a part of my spectrum that it's not caused by orbital variability should not be in the software, because this will make the computation extremely heavy. But with your explanation, I'm thinking that doing that, I can accidentally remove part of the noise that is important for...
Yes.
So it's not a good idea to...
So bottom line is, if you have a trend in your spectrum, the AR1, AR2 thing that you would fit to your spectrum, it's taken care of by the noise in AstroGeoFit. This is a representation in the temporal or depth domain, but it is equivalent to modeling it in the frequency domain.
If for example, I take my data in the depth domain, realize spectral analysis, look the result of the spectral, decrease a little bit the resolution, look again the structure of the spectrum. If they see the same structure, more or less the same cycles. Do you believe that I could use this lower resolution to input to the software to make this computation faster? Or?
But then you would lose information on the astronomical signal.
But assuming that the spectral didn't change too much between this.
Still, you will lose.
Yeah.
I mean, if you take out some of the data, you will take out some of the information. So I wouldn't recommend to do this.
But I think the problem of Thiago is he wants to reduce the computing time. That's mostly what you want. So probably you can, to have a first try, you can reduce it as you want, but at the end, you need to put everything to get the best information.
Yes. If you want a first guess, then yeah, that's fine. Yes. Okay. Okay, so this is, you have your data, you have your model, now you want to fit the model. The first step is the genetic algorithm, and I think one way to think about it is to try to make sure that the algorithm converges. So you have several parameters you can play with: the population size, the number of generations, the number of algorithm solutions, and the list of the number of genes. So what I would do personally would not to try all the combinations of all the parameters, because it takes a long time to estimate. Is just to increase all of those by a common factor until the solutions, the solutions stay the same. So again, the number of algorithm solutions, they will define the number of potential starting points for your MCMC. You will not maybe select all of them to start your MCMCs, but you will select the best of them. So you see that here in these likelihood landscapes, we have a lot of mountains, and they all have similar heights. So you do want to explore most of them. Now, if you had a mountain which is completely dominating, then you don't really care about about the other values of the likelihood. But in this situation, you want a lot of starting points. So yeah, again, so those were removed. You don't have to keep all of them to start your MCMC. But, okay. So, just quick recap of what the genetic algorithm is doing. At step one, you have a population in your parameters in your parameter space, and you want to find the local likelihood maxima. First step is to select the best, the most likely, the fittest parameters, and some of the parameters are selected to reproduce. Then they make new parameters through a mathematical function that depends on the genetic algorithm. Then some of these children mutate, and overall you keep the elites, the selected ones, plus the children with their potential mutations, and then you have your next iteration of the genetic algorithm. So the population size, you can see very intuitively that the more parameters you have everywhere, the better the exploration of the parameter space. So you will have less chance of missing in general. It will increase your chance of finding the local maxima of likelihood. Interesting. Yes. So you see that, so this is a very simple example which converges very quickly. But you see that if you stopped at just 2 iterations, you wouldn't have found the local likelihood maxima. So the number of generations, the number of iterations is related to the convergence of the algorithm. And the number of algorithm solutions is the number of times the algorithm is run. And this is important because from one run of the algorithm to the other, you might end up finding a different likelihood maximum. And so how can you use that in your analysis? Well, you might want to check that when you increase the population number, when you increase the number of times the algorithm is run and so on, the solution that you find, the best solutions you find for the sedimentation rate, they stay the same. So you do your algorithm once, you find this. You increase all the parameters of the convergence, you run the algorithm another time, and you still find those solutions. The thing you want to compute stays the same. That's kind of the definition of convergence. Also, another thing you can look at is the aspect of the likelihood as a function of the number of generations. And what you want is a nice stair-like aspect. You want that for a given number of nodes, you want to reach a point where the solutions don't evolve anymore. So the thing is, if you keep increasing the number of nodes, you will always have a step, which will become smaller and smaller, but you will always have a step. So it's not the idea that at some point, so in that case, this is an ideal case. This is synthetic data, so at some point, adding some more nodes doesn't improve anymore. But in real data, in real cases, you will always have a small improvement. So really, what I'm talking about is for a given number of nodes, before you move on to the next number, you want something that looks very, very still. You don't want something that looks like this. So thanks, Laura, for sending me the plot. Where here you see that at the end of the number of generations for a given number of nodes, you're still trying to improve the solution. This means that the solution has not converged. Yes.
On the previous slide, can you comment a bit on the figure on the left? What are we seeing exactly in the 7th node region? You know.
So it means that now when you move on to 7 nodes, the likelihood increases spectacularly. This is the synthetic data, and it means that from a certain number of nodes, you capture exactly what the sedimentation rate is like. So this was like a very poor approximation, and now you have the flexibility to truly find the correct sedimentation rate.
And what is the dispersion between all the curves? What does it translate to?
Okay. So this translates to the fact that there were several realizations of the algorithm, and some of them converge to a certain local likelihood maximum. Some of them converge to another likelihood maximum. So having a diversity of solution is good.
Yes.
The fact that there is a spread is not a problem.
Okay.
You just want all of these solutions to reach a point where they are in a local likelihood maximum. And when you start from there for the MCMC, or when you do your model comparison, the solution will be there.
Okay. Thank you.
I think a practical question. You mentioned you increase the parameters with a common factor.
Yes.
What does that mean in practice? Like if I double my population, I double my number of genes?
Yes. So this is not. This is just
like a
ballpark, because the thing is, otherwise you might increase the population size and then the number of generations and then the number of times the algorithm is run. You don't want to spend your time checking convergence, you know. So I think it's good to have one process, one for the genetic algorithm. And if this fails, if this simple process fails and you can't find parameters that make the genetic algorithm converge, so in that case, for example, you could reduce the number of the population size. Because if you have the thing is, the bigger the population, the more time you need to bring everyone together to a local maximum. Maybe, yeah, I have to think about it, but yes, I think that's what happens.
Can you go back to the slide with the two figures on it before? No. The number of knots versus... yeah,
one?
that one. So in your opinion, what's the best... For the figure on the left, when is the number of knots ideal?
The number of knots is selected by the AIC. It's not selected at this stage. The number of knots that you select for your model is with the model comparison tool. So this pertains to the convergence of the algorithm, not the decision you make. We'll come back to that. Significance test. Yes, significance test. I think for a I think at this point. So the rationale of this progression is that at this point you're pretty sure that the parameters of the genetic algorithm make it converge. So the result of the genetic algorithm is reliable. Now you use the genetic algorithm for the significance test, and as a first guess, I would run it, but not many times. Just 20 times for the number of noise executions, and a few times for the execution on the data. Because to estimate the null hypothesis, the noise distribution, you estimate a Gaussian. So you don't need a super high resolution on each of the bins. And ballpark, the value of the R squared, the weighted R squared that you'll get on your data will stay the same from one run to the other. So I think it's good to do it at this point because you don't want to start analyzing the data in a lot of detail if there is no signal. But I wouldn't spend too much time on it and just rerun it with 1,000 iterations here and 1,000 iterations here, or 500, to make a good-looking plot in the end. So now you're pretty sure about your genetic algorithm result. You are pretty sure the signal is there. You want to fit your data. And I want to remind you that the genetic algorithm might have trouble converging. So here it started there, and it's going in this way because it finds that the maximum likelihood is maybe this way. And indeed, at some point, it will find a local maximum, still hasn't settled in, still hesitating, where is the maximum? But then at some point, it's like, okay, yes, things start to stay in this region. So in the MCMC algorithm, what defines the number of steps in the chain is length MCMC chain. Discard is how many of the first points you discard. So, when you were in the region where the algorithm was still trying to find its way, you don't want these points. And the thinning is to take one point in the chain every so often. And you want to take a point in the chain every so often because you don't want the correlation of the motion of the walker to translate to a correlation in your data. Because the correlation here has to do with how the inner workings of the algorithm. It doesn't have to do with your data. So again, I would just increase all of this by a common factor until the posteriors stay the same. So you will compute the posteriors with a certain run of the MCMC. You increase the length of the chain. If the posteriors have the same aspect, nothing changes, then this is a good indication that the algorithm has converged. So this is in terms of computational time, what I'm telling you is very inefficient because I'm telling you to run several times the genetic algorithm, several times the MCMC. It's computationally intensive, but it's conceptually simple. It's like you run it several times, you increase the number of iterations, it still gives the same result. I can trust the result of the algorithm. With many asterisks, many caveats, but that's the basic idea. Also, I think it's good to compute the weights of the different maxima. So you know we've seen it many times now that the MCMC explores different parts of the likelihood landscape. And you want to know if this chain matters or not. And then this is the equation that gives you the weight of the chain to tell you if it should matter or not. And you need to run this computation, and I guess the default values work well. Because if you have a chain in one likelihood maximum, another chain in another likelihood, another chain in another likelihood, if you just stack naively the different chains, you might end up with something like this. Now, if you are able to see that one of the chains is dominating, then you will find something like this, which is more, and the thing is, in that case, it's not that we want something which is more precise. We want something which is more reliable. In that case, more precise is more reliable, but you could also find that no, actually you have three solutions, independent, disjoint, and they work equally well. It could happen. It's like sometimes in your equation you have several solutions, and you won't say that one of they just work, all of them. So it means that you can't discriminate between your hypotheses. Okay, so the purpose of all of this is to trust the results of the numerical methods. And I want to stress that this is one of the problems you have, trust the numerical methods. And now you know that the model is retrieving what it's supposed to. But what the model is retrieving is still in the framework of that model. So you still need to have a critical, to observe the results critically. And for instance, we've seen that for the model selection, now we are very sure about our AIC curve. We trust the results, and we want to make a choice on the number of knots. And you can do it based on the BIC or the AIC. And you know that you can trust this value. But you also know that these are two different formulas. Here, the number of parameters is multiplied by the log of the number of data points, and here it's just multiplied by 2. So that's why the BIC tends to select simpler models, because the penalty on the complexity of the model is higher. And so now another question, should we select the AIC or the BIC? Eugene told me that the AIC is usually a little bit more realistic. Usually, in the context of real data, this seems to select a number of knots which is a little higher and which is probably a little more realistic. So that's where your knowledge of the theory can help you interpret the results, and the result of the practice can also help you make a choice. I also want to suggest to use this type of plots for model selection. So now you know that the error bars are reliable, that the solution of the genetic algorithm is reliable. You take it as is because you've ascertained the convergence. And in that case, you see that at some point, the solution, as you keep increasing the number of knots, the solution seems to capture the same things. So, here it's very simple. You start seeing a trend, then other wiggles at a higher frequency. Then this appears, this particular feature appears. And at some point, it seems to stay the same, but just the error bars increase. This is even clearer on this plot. At some point, the results start looking very similar, but just the error bars increase. This is an illustration of the trade-off between simplicity and complexity. Here, very simple model, very simple error bars, but very biased. At some point, you reach the right balance between the flexibility and the bias. So your model is not biased anymore. It's in the correct spot. But if you keep increasing the complexity of your model, you keep increasing the degeneracy between the parameters, so you keep increasing the error bars. And so you see on this plot that from that point on, only the error bars increase, but the model doesn't change fundamentally. So this is another diagnostic that you can use to select the appropriate number of knots on top of the AIC. But suppose the AIC selected this plot, but the best solution would be different for a different number of knots. So it's like the AIC is telling you this, but as you keep increasing the number of knots, the sedimentation rate has not this shape anymore, but it starts oscillating a lot, or then it might just be due to the fact that you find an unrealistic solution, but it might also mean that you have another solution which is more realistic and that you should move on to this other solution.
Can you remind us where do you get the plots of these different knots? Because is it in the MCMC or is it in the...
I guess it's in the MCMC. Right?
Yeah.
It's in the MCMC, okay. This plot. Yeah, it's in the MCMC. But I'm not sure you get... So basically, in two sentences, you want the solution to stay the same and to pick the solution before the error bars start increasing. And this is just a double check with the AIC because this is the same type of model selection. And just like you would like the AIC, BIC to give you the same solution, you would want also this type of diagnostic to be consistent. Okay, so these are some ideas on how to use AstroGeoFit. They are not perfect, but they just convey two very simple ideas. Pay attention to the convergence of your algorithm. And keep in mind that the model is flexible, it's good, it's realistic, but it's not perfect. So you still need to have a critical, to look at your data critically and your results, and not take them for granted. Not just plug the algorithm, let it do its thing, and publish the paper with the results. And that's all I had to say. Thank you. I just want to mention one last thing. So the first author of AstroGeoFit is not here today, and I don't think anybody mentioned his name, Nam, and he's the one who did a lot. He did a lot of the coding, a lot of the conceptual analysis. So we are. I'm very grateful to him for this work. Yes. Do you have questions?
Yeah, so I was wondering if it would be possible at some point to discuss as well that part of the paper with the detection of hiatuses. Yeah.
I can comment on
Yes. Yeah, I think you can comment on this.
Yes, I can comment on this figure. So what we did here, so the problem, and that's a typical comment of referee. And what about the hiatuses? I think it's many geological papers. There will be this question. That's the same kind of question in algebra. They would ask, and what happened in the non-commutative case? And in topology, they will ask what happened on the edge, on the border. Here in geology, the question you can ask, if you don't know anything about geology, you can ask, but what about the hiatuses? Okay, I'm kidding, but here, so the problem is you miss some data, and you don't know how much. Of course, this is a big problem when you count the cycle. When you count the cycle, it's a big problem because you don't know how many cycles you miss. When you look to the precession cycle, you don't know how to reconnect unless you have a very strong modulation, but otherwise it's very difficult. In the case of AstroGeoFit, in fact, AstroGeoFit can overcome this problem in a very efficient way as long as the gap is not too big. Why? It's because it looks globally to the signal. So it will be constrained by the two parts that are on the edge of the hiatus. And this is what you can see here. Maybe I should enlarge a little bit. It would be better if I know how to enlarge this here. Yes, here. So we did this experiment using the constructed, the simulated data. So it is always more easy on the simulated data, but we didn't want to try to make our work too difficult. So this is the analysis with the full data, and it's the full data over 1 million years. You can think it corresponds, it's 1 meter, but can think that it is 1 million years. And so you find this. You find this maybe a little bit. Yes, like that, it's better. So you find the depth time function, and then we cut a piece in the data. Here, 50,000 years, and we just stitch together the two pieces. And here, 100,000 years, and here we stitch together the two pieces. So now, what does, I will look just to the 100,000 year example. What does the AstroGeoFit recover? In fact, what does it correspond to hiatus? It means that the sedimentation is null. So the inverse of the sedimentation is infinite during this time. And so the sedimentation rate is the red curve here, and it goes very high. This is, and then it goes back. In the time depth function, you have the depths, and suddenly you have a jump in time. That's the red curve here. AstroGeoFit will not recover exactly this, but it will be constrained by the two parts that are on both sides, and what it will do, in fact, it will interpolate over the hiatus. So here you see it compensates this big jump by making this bump here, and which allow to interpolate between the two parts, because the signal is constrained here and it's constrained here. That's how it goes. Of course, we'll have to look to that on real data. And yes?
Can we force hiatuses in the data if we know that at some points we have some, but it's too small to cut the data for the convergence regions? But we want to say at this point, sedimentation rate is null, and force the AstroGeoFit to interpolate over it.
I don't understand. You mean if you have a small hiatus or a big hiatus?
Small hiatus.
If you have a small hiatus, you don't care. You just let...
one precession cycle, for example.
Just let the AstroGeoFit go over it without doing anything. The problem would be if you know you have a big hiatus. So that would be different. If you have a big hiatus and you know it, then you may not really in the present version, but you may better say that to AstroGeoFit. In fact, we do it when we have some lack in the data. You just don't show the point. We have example where Eugene analyzed data where you had a big gap between 2 points. You have 1 point here and then another point here, a big gap in depth. So you can maybe in fact, if you know, I'm just thinking in real time. Maybe the good way, if you have a hiatus and you know it and you know the value, you just put the gap in the depth corresponding to the average sedimentation rate. And this will help the software to find the right value. But it's just, I think that's okay. That will be a good thing to do. Now, maybe I can speak of the other part, which is turbidite. Turbidite, that's the correct word. Turbidite. It's the opposite of the hiatus. You suddenly have a big influx on a very short time. So in this case, you know that you have, it will be, it will be, you will have the opposite in the sedimentation, in the depth curve. You have a depth that corresponds to, you have a plateau. You have a depth, instead of a jump, you have a plateau, which means you increase the depth, but not the, it will be the opposite. Here, you have an increase in time without increase in depth. The other one will be a plateau, an increase in depth without increase in time. In the same way, if it is small, AstroGeoFit will manage it without thinking. You have to think too much. But if it is big, it would, and you know it, and you can, because you are geologists, so you can analyze your data, you can remove it. Yes. That would be the most efficient way to use it, probably.
Yeah, so I think what you mean, Jacques, is basically if you have your data as a function of depth and you assume that there is a hiatus here, you just give to AstroGeoFit this data set where you introduced a gap in depth.
Yeah, you introduce the gap. If you know the hiatus and if you know the size of your hiatus, you introduce the gap in the depth that correspond to the mean, an estimate of the mean accumulation rate during this time.
And conversely, if you have a plateau,
you remove it.
You just remove it.
Yeah.
And you give to AstroGeoFit the data where
that would be that would be the way to help AstroGeoFit in case of big gaps or in case of big accumulation. But if they are small, it will just take it in a natural way.
Yes.
You have a question?
Maybe you have remarks also because
I just before I didn't remember. Today I checked. I just realized all the data series I analyzed, I normalized it.
Ah, okay. Okay.
But in theory, the normalization is not necessary, right?
The what?
The normalization of the data series is not necessary.
Yeah. In principle, it's not necessary, but sometimes it, depending on how some of the algorithms, like genetic algorithms, MCMC, they are tuned for a certain range of the data, and normalizing it probably won't do any harm, and maybe it will help.
Yeah, so in general, I just paid more attention to the detrending. I even didn't check whether I normalized or not. Then I checked, I think I normalized all my data series.